Hello everyone, thank you for coming to this talk. My name is Yan. I am an assistant professor at UT Austin. This work is joint with my colleague Junyu. I'm going to talk about a new data acquisition method for recommender systems, specifically designed for the short-form video platforms. The popularity of short-form video platforms exploded in the past few years. In 2020, there are more than 600 million monthly active users in TikTok in China, with more than 100 million monthly active users in the US. By October 2020, TikTok surpassed over 2 billion downloads in App Store. With the increasing popularity and the short video length, there exist extensive new businesses and marketing opportunities. Specifically, short-form video platforms attracted more than 2.1 billion ads in 2018 in China. Because of this, more and more firms joined these competitions, such as Instagram Reels, YouTube Short, Thriller, Class, NetEase, and so on. However, recommendations on short-form video platforms are especially challenging, perhaps even more challenging on other platforms. I'm going to show you two challenges. First, the distribution of interaction data on these platforms typically follow long-tail distribution, similar to other digital platforms. Here is the data collected on the NetEase platform. This is one of the largest music streaming company in China. On the left-hand side, we see the histogram of view time for a month on the NetEase platforms. About 70% of the cards receive no views. On the right-hand side, we see the histogram of the total number of interactions for every user on a given day. And more than 87% of users do not interact with any card. This data sparsity and long-tail distribution issue makes it difficult for recommender systems to understand user preferences. This also makes it difficult for users to discover new content that align with their interest. Meanwhile, new content and niche content creators may be unfairly biased against due to the popularity bias in the digital platforms. This is especially concerning as the competition on the short-form video realm is getting increasingly tougher. Therefore, there is an urgent need to acquire information on user preferences, which is the motivation for this research. Another challenge on these platforms is that these music video contents rapidly evolve. New trends surface and outdated content no longer appear. Here is another example. The X and Y axis show the total view time for each topic on NetEase on the beginning of November in 2019 and end of the month. The points lower than the diagonal line correspond to topics with decreasing popularity, and the ones above the diagonal line shows the ones that with increasing popularity. So you can see that the points lying on the x-axis are topics that receive no review by the end of the month, but they are pretty popular on the beginning of this month, which means that these cards become out of date. On the y-axis, we also see points that receive no views on the beginning of the month, but becomes popular by the end of the month. So these are the new topics that emerges. This shows that the future distribution rapidly changes on this platform. However, most bandit methods assume that data distribution of acquisition and implementation period are the same, while we see from this plot that this assumption does not hold. Therefore, those non-transductive methods cannot adapt timely to the new video trend, which is the pinpoint for many social media platforms. Let's start from an overview of the result. We introduced a new pure exploration problem for data acquisition on short-form video platforms to find an optimal set that account for user heterogeneity and also the change in feature distribution. Second, we propose an adaptive data acquisition method that can simultaneously collect data samples, split the user feature space to account for user heterogeneity, and remove suboptimal items. We also proved the prediction error bound within each user being. Lastly, we demonstrate the effectiveness of the method using data collected on the NetEase platform that greatly outperform the state-of-the-art bandit benchmarks. On platforms usually face an exploration versus exploitation dilemma. We need to get good information about the environment to be able to take good actions. In this problem, we use a sample of measurement sets to learn user preferences in the exploration period, and then we want to design a personalized recommendation policies that can be implemented in the exploitation period. We introduced a new pure exploration problem for data acquisition for finding a new optimal set. So in this optimal set, we have K, that is the capacity of the platform, which is restricted by the platform's interface capacity and user attention span. That is, we will select at most K personalized content for a recommendation at each time. We also have a tolerance level, which is this epsilon h. That is, for all the cards that we identified, we want to make sure that they are tolerable. Take the short form video as an example. We want to make sure that there is at least certain view time on the cards that we recommend. And we also specify the precision level. That is, we want to find all the cards within the precision level. For example, let's say the optimal music card can receive a 1 minute view time and our precision level is set to be 10 seconds. That means that we want to find all music cards that have more than 50-second average view time. I'll give you a quick overview of our model and theoretical result. We first derive the prediction error bound as in this theorem. For a fixed user being, we show that the prediction error is bounded by the sum of observational noise and the impurity of the user preference theta. And with this result, our next task is to design an algorithm that can adaptively split the user space so that we can reduce the impurity of theta and collect more data points. Therefore, we can reduce the observational noise. Now let's take a look at our allocation rule. We first need to discuss how to identify an optimal set for a targeted data set Z. Given that allocation rule, phi can be specified in this function. We have two conditions on the minimum sample size and the maximum allowable impurity. With these two conditions, we can identify an optimal set with high probability. And then we can design the optimal static allocation rule, that is the proportion of cards to sample with feature X. Looking at the allocation rule, we'll see that this important theta u is unobserved. And therefore, we propose an algorithm that sequentially removes suboptimal arms until an optimal set is identified. Specifically, we split the time steps into epochs. During the epoch, we collect data points. When the epoch completes, we remove suboptimal arms with gap larger than this threshold. Now let me summarize and talk about our algorithm. Our algorithm is called adaptive acquisition tree. It simultaneously collects data and split user space based on the features. We keep track of the epoch index and the number of samples collected for each bean. If enough samples in the bean are collected for each epoch, we check if the impurity condition is satisfied. If it is not satisfied, we would split the bean to children beans and they inherit the active arm set from parent bean. On the right hand side, here's an example of how we do this adaptive split. We will do this adaptive split if the impurity of theta condition is not satisfied. If it is satisfied, that means that the current epoch is completed, and then we will remove suboptimal arms and then update the allocation rule and the next epoch starts. At the beginning of epoch L+1, we again check if the impurity is satisfied. If it is not satisfied, we'll split the bean according to the feature importance rule. Let's talk about our experiments. We use the data collected on this NetEase cloud platform, which is the same data that I showed you in the motivation. In the experiments, we remove cards and users whose overall view time is below 6 60 seconds. This left us with more than 6,000 users and more than 3,000 cards. We have two experiments. The first one want to find the optimal set for spotlight recommendation. So in spotlight recommendation, typically one card will be spotlighted on the platform main page. And the second is the top K recommendation. We want to find the top K card with the optimality guarantee. Since we do not observe user behavior on cards they are not exposed to, we simulate their responses. In our first spotlight recommendation example, the metrics that we look at include the proportion of best card identified, the AUC in identifying the best card, and expected view time per user. For these three metrics, the larger the value, the better. So our method is called AAT. You see that our method performs much better in comparison with other state-of-the-art benchmarks. The second experiment is on this optimal set. Specifically, we specify the K to be 5, the tolerance to be 0.6, precision to be 0.4. You see that we perform much better than the other benchmarks. Now let me conclude. We introduce a new data acquisition problems that is specifically developed for short-form video platforms. Our method can account for user preference heterogeneity, and more importantly, it can account for the transductive settings. That is, if the feature distribution of the exploration and exploitation set are not the same. We propose a new pure exploration problem, and the goal is to find all arms that are within certain optimality gap relative to the best arm, and we don't want to find arms that are outside of our tolerance level. We demonstrate the effectiveness of our algorithm on the NetEase platform. Note that the method developed for the short-form video platform in our project can be used for other digital platforms, as our method can capture the fast evolving trend on these platforms. Thank you for your attention.